All right, this is section 5.3. We're looking at independence and the multiplication rule, and we're dealing with probabilities. Usually in probability, when you see the word and, that's going to be attached to the multiplication rule. And we're going to be looking at, again here, independent events. So we're going to identify independent events, use the multiplication rule for the independent events, and then compute what we call at least probability. So at least 2, at least 7, at least 1, things of that nature. But first, how do we identify independent events? So we use the addition rule for disjoint events to compute the probability of observing an outcome of the probability of E, or event E, or event F. So that was the addition rule, was with or. Now we're going to talk about computing probabilities for the event that E and F both occur. Okay, now before we can present this rule, we got to talk about this idea of independent events. So two events, E and F, are independent if the occurrence of event E in a probability does not affect the probability of event F. Okay, so an example would be, if you roll two die. The outcome of the first dice is not going to affect the outcome of the second. Same thing if you flip a coin twice, same thing. Those are independent. The first does not affect the second. However, two events are dependent if the occurrence of event E in a probability experiment affects the probability of event F. So simple there is, say you have 10 marbles in a drawer or in a bag or something. You draw out one marble and you do not replace that marble. Then you draw another marble. That second marble, the event, is dependent upon what you selected on the first, because now you've changed the sample space. So I've kind of given you a couple of ideas here. But again, just think about if you flip a fair coin, you flip it twice. Does the fact that it lands on heads first have any effect on the likelihood of it landing on heads second? Okay, not unless you are a master coin flipper who can manipulate the outcome of a coin flip. Okay, it's because the first flip is completely independent of the second. Those outcomes are independent. Now, disjoint events versus independent events. Okay, they are different concepts. Okay, so recall that two events are disjoint if they have no outcomes in common. Okay, that was disjoint. That is knowing that if knowing one of the events occurs, we know that the other event did not occur. Independence, however, means that one event occurring does not affect the probability of the second. So hopefully you can see the difference there. So knowing that two things are disjoint does not imply that they are independent. Okay, so just be cautious of that. Okay, so let's determine whether or not a couple of these are independent or dependent. So the first one, event E, the battery in your cell phone is dead, and F, the batteries in your calculator are dead. Okay, well, the fact that the batteries in one device are dead does not affect whether or not the batteries in another device are dead. So those would be independent events. Okay, because the probability of one happening does not affect the probability of the other. Okay, the second one, your favorite color is blue. Your friend's favorite hobby is fishing. Okay, your color is not going to affect the hobby or your friend's hobby in fishing. So those would be independent as well. Okay, and then part C, you are late for school and your car runs out of gas. Okay, these would most likely carry some dependence. So we call these dependents because if you're late for school, and your car runs out of gas, there's a good chance that those two are one's dependent upon the other. If your car runs out of gas, you're probably going to be late for school. So here's the multiplication rule, and this is only for independent events. Okay, and in the next section, we're going to talk about what happens if they become dependent. But if they're independent, then the probability of event E and F occurring is just the probability of E times the probability of F. Okay, so this first one we have, suppose that E and F are independent. The probability of E is 0.7, the probability of F is 0.9. What's the probability of E and F? Okay, if they're independent, then we would just multiply those two probabilities together, 0.7 times 0.9, which is 0.63. And that would be the probability of events E and F occurring. Okay, the multiplication rule for independent events, when you have n different independent events, so if we've got events 1, 2, 3 on up to n, they're all independent of one another, then the probability of E1 and E2 and E3 and up to En and so forth, it's just the probabilities all multiplied together of each individual event. As long as they're independent. Okay, again, that's the key thing that we're talking about in this lesson, is everything right now is independent. Okay, so what's the probability of obtaining 4 ones in a row when rolling a fair 6-sided die? So if you're going to roll a fair 6-sided die 4 times, we want to know what's the probability you get a 1, and then a 1, and a 1, and a 1. Okay, so you roll it, you get a 1. Pick it up, roll it, get a 1. Hopefully you can see that those are independent. Then this is just going to be the probability of getting a 1 times the probability of getting a 1 times the probability of getting a 1 times the probability of getting a 1. Or in this case, the probability of getting a 1 raised to the 4th power is one way to look at it. But the probability of getting a 1 is 1/6, 1 out of 6 on that dice. So you do 1/6 times 1/6 times 1/6 times 1/6, which gives you 1 out of 1,296. So very, very low likelihood of rolling 4 ones, but there is a probability. It could happen. Okay. Next, we're going to look at false positives. So the ELISA is a test to determine whether the HIV antibody is present. Okay, the test is 99.5% effective, which means the test will come back negative if the HIV antibody is not present 99.5% of the time. The probability of a test coming back positive when the antibody is not present, which is called a false positive, is 0.005, which is the complement of the 99.5%. So suppose an ELISA test is given to 5 randomly selected people who do not. So we know they do not have the HIV antibody. Okay, the first one is, what is the probability that the ELISA comes back negative for all 5 people? Okay, so they don't have HIV. So given that they don't have HIV, the probability of getting back a negative test is 99.5%, or 0.95. Okay, and we're going to be using 0.995, for our probability here, for our calculations. So this is the probability that you get 5 negatives, which is going to be a negative for the first, times the negative for the second, times the negative for the third, so on and so forth. So we'll just do 0.995, and this will be raised to the 5th power, instead of writing that all the way out. Okay, which is 0.9752. So there's a 97.52% chance, or 0.9752 probability, that the ELISA test will come back negative for all 5 people. Now, what's the probability that it comes back positive for at least 1 person? Okay, now let's think about this for a minute. Okay, if you're positive for at least 1, so the probability that at least 1 is positive. So that could mean, you have the first person's positive, and then the next 4 are negative, or the second's positive and the 4 around them are negative, or you could have 4 positives and 1 negative. But it says, what's the probability that at least 1? So at least 1 gives you all kinds of scenarios. So we are going to look at the complement of this. So the probability of at least 1, its complement is 1 minus the probability. And if you think of the complement of at least 1, that complement would be none. That means, in our case, that none come back positive, or, in other words, they all come back negative. We found that probability that all 5 were negative up here, so the probability that at least 1 comes back positive would be 1 minus the 0.9752, that probability that they're all negative. Okay, and that equals 0.0248. So there's a 0.0248 probability, or 2.48% chance, that at least one person would come back positive, even though they are negative, in this group of 5 people. Okay, that's the power of using this idea of the complement. And this is the idea of looking at least 1. Just remember, this is a very, very big idea here, that the probability of at least 1 is 1 minus the probability that none occur. That will be used very frequently in this class. Okay. So in this one, driving under the influence. So among 21 to 25-year-olds, 29% say they have driven while under the influence of alcohol. That's comforting. So suppose that 3 21 to 25-year-olds are selected at random. We just randomly select 3 people in that age group. What's the probability that all 3 have driven while under the influence? Okay, so this is the probability that all 3 have driven under the influence. Okay, well, the probability for each of them is 29%, so this would be 0.29 times 0.29 times 0.29, or 0.29 to the third power, which is 0.0244. So if you randomly select 3 people in that age group, there's a 2.44% chance, or 0.0244 probability, that all 3 that you select have driven under the influence of alcohol at some point. That was part A. Part B, what is the probability that at least 1 has not driven while under the influence? So probability at least 1 has not. Okay. Then that, again, we're going to use the complement here. This would be the probability that, 1 minus the probability that all 3 had driven under the influence. Again, when we're looking at 3 individuals. Well, we know that probability, so it'll be 1 minus 0.0244, which is, let's see, 0.9756. So there's a 0.9756 probability, or 97.56% chance, that at least 1 has not driven while under the influence. Okay. All right, part C, what's the probability that none of the 3 has driven while under the influence? So this is the probability that none of the 3 have driven while under the influence. Well, if there's a 29% chance that an individual says they have driven while under the influence, then the complement of that would be 1 minus 29%, or 71%. So it would be 0.71. And if all 3 have not, then you would just do 0.71 times 0.71 times 0.71, because we're randomly selecting individuals, so we can assume they're independent of one another. So this is 0.3579. So there's a 37% chance that all 3 people you select, or 35.79% chance that all 3 you select will have not driven under the influence. Okay, part D, what is the probability that at least 1 has driven while under the influence? So probability at least 1, I'll just say 1 drove under the influence. This would be 1 minus the probability that none drove while under the influence, which is 1 minus that 0.3579. Again, we're just using that complement rule, which is 0.6421. Okay. So that's a look at, again, hopefully we can all agree that these, if you randomly select 3 people out of any group, any person 21 to 25, there's high likelihood that they are independent from one another. And so if you have any questions, let me know and we'll continue on to part 2.